Hello students, welcome back to another calming video series with Mr. Charvella. This time we'll be talking about activation energy, collision theory, and catalysts. Um, so we'll just kind of go through this piece by piece here. So starting off with activation energy. Activation energy is the minimum amount of energy required for a reaction to take place. So if we kind of look at this picture here, there's this guy that's trying to putt into the onto the green, so he has to get over this hill first. So he has to put in enough energy to get over that hill before he can get to the other side of that hill. So you can think of it as a barrier. If particles don't have enough energy to get over this hill, then they're just going to fall back down to where they were. The same thing that ball would, if you didn't put enough energy into it, it's just going to roll up part of the hill and come back to him. So we can look at this in terms of reactants and products. So if reactants don't have enough energy to make it up the hill, then they just go back to being reactants. They might collide and try to become products, but if they don't have the energy required to get up to this point, then they're never going to make it over here. So that's essentially what activation energy is. It's the amount of energy required to get from this reactant side of everything to the product side of everything. It's usually delta E. When we get to thermo, we'll also talk about it as delta H, so heat of reaction. And then it will give off a certain amount of energy at the end if the products have a lower energy position than the reactants. So you can see the reactants are up here. You can see, like, here's how much energy the reactants have just stored in them. And if we compare that to the products have less energy stored in them. They're more stable, if you want to think of it that way. So they give off this extra energy as heat. So that would be an exothermic reaction because you have this extra heat let off that's happening here. An endothermic reaction would be one where the products end in a position that is higher in energy than the reactants are, so they actually absorb some of that extra energy. But we'll kind of talk about that as we kind of get going here. So the activation energy part of everything is this EA part of the graph. If you take the energy that the reactants have stored in them and take it to the peak of the graph, so the difference from where the reactants are starting to where they would need to be in order to break bonds, this is the activation energy. So you can kind of think of it as cresting this hill, or just this line from here to the peak. So this EA that's right here. The energy that is released from those new bonds is this. So you get back this activation energy. If the products are lower energy than the reactants, then there's this extra energy that you're releasing. So this is the released energy right here. This is given back to the system to help other things reach activation. So that's kind of the general view of this whole thing. And then last but not least, if we have if we have a multi-step process, or like if we're creating a momentary complex, we call that a transition state right up here. So activation complex or transition state. So this is kind of where everything's coming together at once. You haven't fully, you're still breaking and forming new bonds, so everything is kind of in flux. So the bonds are all broken and reforming new ones. You might also have like an intermediate species that we'll talk about later on that will appear here. So there's that kind of bit behind everything too. So this is just the transition state. When we start talking about multi-step mechanisms, this will break up and we'll see kind of more of what a transition state truly looks like, but this is just a momentary flux. So that kind of gives us this general reaction pathway. So the EA is the energy required to reach that transition state. And when you're labeling this thing, you have to make sure that the line that you're drawing, so you draw this dotted line here, you have to make sure that any labeled arrows go all the way from top to bottom. So you need to label it all that way as EA. If you were to just do something along the lines of this, AP doesn't like to see that, and honestly, we don't like to see it either. And this arrow implies that the energy from here to here is the activation energy, which it's not, because you need to go all the way to the peak and all the way down. So just make sure that you guys are doing stuff like that. The let-off heat too, so there's not a whole lot, but if we were to draw this dotted line, like there's a little bit of heat that's being let off. So this is our exothermic. So you'd also have to draw that full arrow, but here it's only a pretty small gap. So looking at this one, let's talk about exo versus endo and what is the slowest. So as I already said, exo is one where the products have a lower energy position than the reactants. So if this is our products and these are our reactants, that's a bad P, let's fix that. So same thing, products here, reactants here. These two are both going to be exo because the products have a lower energy profile than the reactants, so they give off extra energy. So this one's exo, so is this one. And then the last one is endothermic. And I'm writing with a mouse right now, so you'll have to, or actually trackpad, so you'll have to excuse how slow I'm doing this. So this is going to be endothermic because our this extra little bit of energy is actually being stolen by the products because they're storing it. So this is stored energy by the products and so forth. So it's stealing it from the environment. So the environment actually needs to keep putting in more and more energy to keep meeting this activation because it's not getting that activation energy back. So this is endo. Now if we're talking about slowest reaction, slowest reaction is going to be the reaction that has the largest activation energy. So right here, this guy requires 25 kilojoules per mole for activation energy, while this one's only 20 and this one's 15. So this one is actually probably going to be the slowest reaction because essentially raw reactants have to crest this entire thing. So every reactant has to have extra energy to get up to the peak here, whereas these guys need noticeably less energy. Actually, before I move on, the other thing worth talking about here is some reactions are reversible. Most reactions actually are reversible. So it's possible for this thing to flip backwards and like taking this one into context. Now this side would become the reactants and this side would become the products. So now this guy has this whole big activation energy to get over, whereas this one is smaller and smaller here. So this is actually the smallest reverse activation energy. So this one probably is a bit more reversible than these guys are because this is such a steep peak as far as the reverse goes. This is probably far less likely to go in reverse. And so if it had an equilibrium, the equilibrium would definitely favor the products more likely than the reactants. But that's something we'll talk about when we get to an equilibrium unit. Okay, that brings us to collision theory. So in collision theory, there's a handful of things that have to happen. A, particles must collide. Pretty straightforward. Only two particles may collide at one time. So you shouldn't have three particles all trying to hit each other at one time. It gets messy, and it's far less likely to happen statistically. those particles also need to have the correct orientation. So if you think of a water molecule trying to react with, it really doesn't matter. Let's say that water molecule, it is the hydrogens on that water molecule that's reacting. If your oxygen is what's bumping into everything, then hydrogen isn't going to have the opportunity to react the way it needs to. So it's the correct part of the molecule that should be colliding. And then they need to occur with enough energy. So that's the activation energy. So they need to have enough energy to break their existing bonds and then to form new bonds so that they can kind of rearrange. So 4 major things: must be colliding, only 2 at a time, proper orientation with enough energy. So here's the general collision model. So before the collision, here's this molecule, here's this rogue element. This element needs to collide with the other green part of this molecule for the reaction to take place, so that's the orientation. They have to collide with the proper amount of energy, so if there's not enough energy here to form a new bond and break this bond, nothing will happen. But if there is the energy, if they are making that activation energy, they will split and cross everything. This right here is our transition state. So this temporary moment where you have this bond forming and this bond breaking and this whole thing's in flux and it becomes like one giant molecule, that's a transition state. And then it can either fall back down to the reactant side or it can go over to the other side of the graph and make products. So we'll do a demonstration with thermite balls in class if we haven't already, which by the time you guys watch this video, I would think we will have done it. But either way, we'll do it, and it kind of shows that whole collision energy thing, but know that this is coming if you haven't seen it yet. Temperature and rate. So the other thing that's worth talking about in all of this is how temperature affects rate. So generally, as temperature increases, so does the rate of the reaction. That's usually kind of an assumption. Not all reactions are that way, but most common reactions increase this way. This is because K is temperature dependent. So essentially, there is a different K value at different temperatures. As far as this goes, the only thing you really need to know is that there are different K values for different temperatures. There's also this fun thing called the Arrhenius equation, and you can notice that I didn't write the equation for you because you don't need to know it. So the nicest thing about the Arrhenius equation is you guys just need to know that it exists and that it can be used to solve for K at different temperatures. So you determine K experimentally at several temperatures. You can then use that to calculate activation energy, but you don't ever need to do this. It's not like a major thing. You guys don't ever have to deal with the Arrhenius equation. So you just need to know that it is a thing, but we and AP will never expect you to solve it. So that brings us to Maxwell-Boltzmann distributions. So you can see that these were all kind of activation graphs, sort of looking things. These are actually a bit different. So these are representing particles, and they are comparing 2 substances, or in this case 3 substances, or possibly 1 substance at several temperatures. So kind of going back, temperature affects rate. So we can either look at 1 substance at different temperatures, or we can look at 3 different substances just to see what the activation profile, or which ones are activating more than other ones. I also didn't mention this, but one thing that you can do to kind of prove that temperature affects rate is crack a glow stick and throw 1 in hot water and 1 in cold water, and you'll actually see that the 1 in hot water will glow brighter than the 1 in cold water. It's kind of a cool thing. So the whole point of this graph is to compare either 3 gases at 1 temperature or 1 gas at 3 different temperatures. Well, you can see this one's labeled with 3 different temperatures, so we're going to go and assume that we're dealing with 1 gas at 3 different temperatures. The general idea of these kind of graphs is that we are seeing how much or what percentage of that substance is reaching activation energy, whereas the other one, like what percentage is the colder substance reaching activation energy. So as an example, let's talk about ice cream. So if we're dealing with ice cream, it is going to melt at room temperature. Actually, it's going to melt at anything above freezing point. And the freezing point of water in Kelvin is 273. So if we were to look at this temperature, to say this temperature is 273, a certain amount of that ice cream will have enough energy to be in a melted state. So if we are dealing with, ice cream where the average temperature is 100K, well, some of those ice cream particles will have slightly more energy than the rest of the ice cream, so some of it will be slightly melted. If we're talking about at where the average is 200K, well, now we're closer to the melting point, so some of those particles, again, will have more energy than the others. And then if we're talking something like 400K, which is as an average, rather unrealistic, then we should actually have even more of that substance melted. Like, I'm just kind of using that as an example, just to get you guys thinking about it, but like, it's a good starting point. So that being said, the general idea here is that one graph is going to show a greater amount of its, a greater percentage of its substance as being activated. So if we're comparing T1 and T2, which is greater than T1 here, this line right here is a higher average temperature. So more of the graph reaches this activation phase and is activated enough to collide with the proper amount of energy. Here, the average energy is colder because T1 is smaller than T2, and so less of that graph is activated, less of that substance is activated, so the reaction rate will be slower because there's not as many particles that have the proper activation energy. So the two big things that you can notice from these graphs, even though this graph right here is shorter, it's shorter because it's more spread out over a range. So that means the activation energy is more spread out because it has a higher average. So the shorter the graph is, the higher the average temperature or average activation energy there is. The taller, the less particles are going to be activated because it's scrunched more towards the left side of this graph. So if I were to add a third temperature profile in here, and that temperature profile was even colder than T1, that graph would need to be even taller than T1 and more to the left. And then when it comes down, you'll see it actually swoops lower than T1 and T2 do on this activation side because even less of it is going to be activated. So this has been a question in the past on the AP exam where it's like which of these graphs makes sense. You want to look for one where the higher the peak is, the colder it's representing or the less activated it's representing. So taller peaks should be more to the left. They should represent a colder temperature or less energy. And when they swoop down, they should cross these two other graphs and swoop beneath them. So something that you shouldn't see, you should definitely not see anything that ever like pulls one of these numbers because that like doesn't make any sense. There's no way it has a lower average but more activation. It's not a thing. Okay, so from there, this is sort of what I've been kind of talking about. So if this is our activation energy right here, this right here, everything under this graph represents all the particles, the percentage of particles that aren't reaching that activation energy. They're missing the energy. And up here is representing the handful of particles that do reach activation energy. They have enough energy to collide with and break or form bonds. The greater this percentage is, the faster this thing's going to react. So we can look at this one. Now we have, again, the same idea, so 3 different temperatures. The colder temperature peaks up higher on the left-hand side, swoops down, less activation in terms of number of particles, whereas the 100 degree Celsius line is lower than the others because it's spread out. The average is now spread out. The average is reaching farther left farther right on the graph profile, and more of it is in the activation area. So essentially, as you increase temperature here, then you're also increasing energy. There's a higher percentage of particles that have the correct number of energy, or high probability that when particles collide, they will have the correct amount of activation energy. We can also look at this as multiple different gases. So argon versus neon versus helium. So helium is a lighter molecule. So even though these are all at the same temperature, because helium is lighter, it has more kinetic energy because it's a smaller molecule. It's easier. It doesn't take as much energy to move as quickly. So that molecule will have a higher it will be able to collide harder, like when it hits. So because it'll be moving faster, so at the same temperature it can collide more frequently and also with more energy than neon would, because neon's heavier, argon's even heavier than that. So even less of that will be activated or have the correct amount of kinetic energy at that temperature. Okay, so looking at this problem, this is from AP in 1998. So on the diagram below, we just need to label everything. So if these are our reactants, and we just plugged in values here, if these are our reactants, draw the dotted line across, and from here to the peak is our activation energy. And then the difference in energy from our reactants to our products is our delta H, which is how much energy is being released. And since it's releasing more energy than, like, the products are lower energy than the reactants, it's releasing this extra delta H, which is why it's exothermic, and has this negative energy value. Okay. Last thing to talk about in this whole thing is catalysts. So as far as catalysts go, the whole point of a catalyst is it lowers the activation energy. So there's less activation energy required. It does this by changing the way the reaction works. So what things have to hit what things, and it generally makes an easier pathway. So catalysts lower this EA requirement. They make the activation energy requirement smaller, so it's a smaller hump, so it's easier to get over. It is a completely different problem. So it has its own K value, it has its own rate and everything else. Like, it's a completely different mechanism. So the only comparison between a catalyzed reaction and an uncatalyzed reaction is you have similar reactants and products, but the way that reaction is taking place is different. So since it has a lower activation energy, if we look at the uncatalyzed reaction, if this is the activation energy in the Maxwell-Boltzmann, here's the amount of particles that meet that energy requirement. Well, a catalyzed reaction lowers this requirement, so even more particles now reach that requirement, and so this rate of this reaction should increase because of that. And that's pretty much the gist of everything. So we'll talk about this in class. Some of this will make more sense after we do the demo and after you guys get a little bit more practice with it. I would assume that those Maxwell-Boltzmann ones are probably going to be the ones that confuse you guys the most, but we'll kind of talk about that and deal with that a little bit. Beyond that, thank you for sitting through all of this, and I hope you have a lovely rest of your day.